Welcome! In this session, we will explore a fascinating problem called custom sort string. It involves sorting characters of a string based on a custom order provided as input. We'll dive into the problem statement, break down the solution approaches, and analyze their complexities. Let's get started. In this problem, we are tasked with reordering the characters of a string based on a custom order defined by another string. Specifically, you are given two strings, order and s. The string order contains unique characters, and it defines the sequence in which characters should appear in the output. Your job is to rearrange the characters of s to match this custom order. Any characters in s that are not mentioned in order can be placed anywhere in the result. For example, if order is CBA and s is ABCD, we rearrange s so that C, B, and A appear first, in that order, followed by any characters not specified in order. The result would be CBAD. In terms of input constraints, order can have a maximum length of 26, as it only contains unique lowercase English letters, and s can have a length of up to 200 characters. The goal is to return the reordered version of s as a string. Let's look at an example to make this clearer. Suppose order is CBA and s is ABCD. In this case, the characters in order C, B, and A determine the sequence. From S, we first pick C, then B, and then A, in that specific order. The character D is not part of order, so it can be placed arbitrarily. When we put it all together, the reordered result is CBAD. Another example is order equals QEP and S equals PKEK. Following the sequence defined in order, we arrange K, Q, E, and P from S. The extra E, which is also part of S, is placed next to maintain the relative order of characters not explicitly defined in order. The result is KEEP. These examples demonstrate how the characters from order act as a priority sequence while handling the rest of the characters flexibly. Here's one more example to solidify the concept. Imagine order is XYZ, and S is ZYX. The custom order tells us to prioritize X, Y, and Z in that order. Looking at S, we see that each of these characters appears twice. So, we first arrange the X's, then the Y's, and finally the Z's, preserving their frequencies in S. The result is XYZ. This example highlights how the custom order dictates the placement of characters while considering their counts in S. When a character appears multiple times, we include all its occurrences in the correct order, ensuring that the output string respects the priorities defined in order. Now let's consider the constraints and some edge cases. The length of order ranges from 1 to 26, and all its characters are unique. The string S is between 1 and 200 characters long, consisting only of lowercase English letters. One edge case is when order and S have no overlapping characters. For example, if order is ABC and S is XYZ, none of the characters in S are in order, so the output can simply be XYZ, with the characters arranged arbitrarily. Another case is when S contains duplicate characters that are part of order. For instance, if order is ABC and S is ABC, the result would still follow the same sequence as order, producing ABC. Finally, if S contains a mix of characters both in and out of order, such as order being XYZ and S being ZYZABC, we prioritize X, Y, and Z first based on their frequency in S, and then append the remaining characters at B and C arbitrarily. These scenarios help illustrate how the problem can handle a variety of inputs while maintaining the rules defined by the custom order. To begin, we considered the brute force approach, which relies on directly iterating through the characters of the order string. For each character in order, we find all occurrences of that character in the string S and collect them in the result. Once we've processed all characters in order, we append any remaining characters in S that were not included. While this approach is straightforward and easy to understand, it's inefficient for larger inputs due to its nested iteration. Specifically, the time complexity is O, n*m, where n is the length of order and m is the length of S. Since we examine each character in order and for each one check all of S, this redundancy makes it slow. Additionally, the space complexity is O, n plus m, to store the result string, which may also be a concern for very large inputs. To address the inefficiencies of the brute force approach, we can optimize the process by using a hash map to store the frequency of each character in S. By pre-computing these frequencies, we can directly construct the result string in a much more efficient manner. Here's how it works. First, we count how many times each character appears in S and store these counts in a hash map. Then, we iterate through the order string, and for each character, we check its frequency in the hash map. If the character exists, we append it to the result string a number of times equal to its frequency, and then remove it from the hash map. Finally, we append any remaining characters in the hash map, those not found in order, to the result string. This approach reduces the time complexity to O, n plus m, as the hash map operations allow us to avoid nested loops. The space complexity remains O, n plus m, due to the hash map and the result string, but it's a significant improvement in terms of execution time for larger inputs. Another possible solution is to use a sorting-based approach. Here, we define a custom sorting order based on the order string. Each character in order is assigned an index, which determines its priority during sorting. For characters in S that are not found in order, we assign them the lowest priority. This way, when we sort the string S, it will automatically follow the sequence defined by order. While this approach is intuitive and leverages built-in sorting functions, it is less efficient than the hash map-based solution. The sorting process requires O, m asterisk log, m, time, where m is the length of S, and creating the custom mapping for order takes O, n. Thus, the overall time complexity is higher compared to the linear time achievable with the hash map method. Additionally, the space complexity is O, n plus m, for storing the mapping in the sorted string. After evaluating the different approaches, the hash map-based solution stands out as the most efficient and practical. By pre-computing the frequencies of the characters in S, we can construct the result string directly in linear time, avoiding the nested iteration of the brute force method and the overhead of sorting in the alternative approach. The key insight here is that the order string provides a fixed sequence, allowing us to append characters directly in the correct order without needing to sort. Using a hash map for frequency lookups ensures quick access and reduces the overall time complexity to O, n plus m. As a result, this approach balances efficiency and ease of implementation, making it ideal for both competitive programming and real-world applications. While the brute force method is simpler conceptually, it doesn't scale well to larger inputs. Similarly, the sorting-based approach, though intuitive, is less efficient due to its higher time complexity. In conclusion, the hash map approach offers the best balance of efficiency and simplicity, making it the most practical solution for solving this problem. By leveraging frequency counts and directly appending characters in the order specified, we achieve optimal performance while keeping the implementation straightforward. This makes the approach both scalable for large inputs and easy to adapt for similar problems. To solve the problem, we need to reorder the characters in the string S according to the order defined in the string order. Any characters in S that are not listed in order should be appended to the result, while maintaining their relative order in S. The brute force approach begins by iterating over each character in order. For each character, we scan through S and collect all its occurrences, appending them to the result. For example, if order is CBA and S is ABCDACB, we start by collecting all occurrences of C, followed by B, and so on. After processing all characters from order, we handle the remaining characters in S that are not in order. These are appended to the result while keeping their original sequence intact. Finally, the constructed string is returned as the output. The final step in the brute force approach is to append any remaining characters from S that were not included while iterating over order. For instance, in our example with order equals CBA and S equals ABCDACB, the character remains after processing C, B, and A. This results in the string kebad. The pseudocode for this process is straightforward. We use a nested loop to match characters from order with those in S, appending matches to the result string. Afterward, a second loop appends any unmatched characters to the result. This method is simple but inefficient, as it involves repeatedly iterating through S for each character in order, leading to a time complexity of O, m asterisk n, where m is the length of order and n is the length of S. The brute force approach has some clear benefits and drawbacks. On the positive side, it ensures that the characters in S are reordered exactly as specified by order. Characters not in order are appended in their original order, preserving their relative positions in S. However, the inefficiency of this method stands out. Since we iterate through S multiple times, once for each character in order, the time complexity is O, m asterisk n. Additionally, the use of string concatenation makes the approach slower, as each concatenation creates a new string in memory. To optimize this, we can consider using better data structures. For example, a set can be used to quickly check whether a character is in order, reducing the lookup time from O(m) to O(1). This observation motivates a more efficient solution. To address the inefficiencies of the brute force approach, we can use a frequency map and an ordered traversal. First, we build a frequency map using a dictionary to count the occurrences of each character in S. For example, with S equals ABCDCB, the frequency map would be A2, B2, C2, D1. Next, we iterate through order and append each character to the result string as many times as it appears in the frequency map. Using the earlier example, if order equals CBA, we append CC4C, BB4B, and AA4A to the result. This ensures that all characters from order are added in the correct sequence, while efficiently handling their counts using the frequency map. After processing all characters in order, we handle any remaining characters in S. These are the ones that were not included in order. We iterate through the frequency map and append them to the result string. For instance, if the remaining character is D with a frequency of 1, we append it to the result. The optimized pseudocode reflects these steps. We begin by calculating the frequency of each character, then construct the result string in two stages, first by traversing order, and then by appending the remaining characters. This approach is significantly more efficient because it avoids repeated scans of S and uses a list for result construction, which is faster than string concatenation. The optimized solution has a much improved complexity. Building the frequency map takes O(n), iterating through order is O(m), and appending the remaining characters is another O(n). This gives a total time complexity of O(m plus n). The space complexity is O(n), as we store the frequency map and the result list. This efficiency makes the approach suitable for large inputs. Regarding edge cases, if either order or S is empty, the result will simply be S. If there is no overlap between order and S, the result remains identical to S. Duplicate characters in order are ignored after their first occurrence, and the algorithm handles large strings well due to its linear complexity. This ensures robustness across a variety of input scenarios. This is the solution to LeetCode problem number 791, custom sort string. The goal is to rearrange the string S based on the order of characters in the string order. Any characters in S that are not present in order should appear at the end of the result while preserving their relative order. The method starts by creating a frequency map, a dictionary, to count the occurrences of each character in S. This is done using a simple loop that iterates over the characters of S and updates their count in the dictionary. Next, the result string is constructed by iterating over the characters in order. For each character in order, if it exists in the frequency map, its occurrences are added to the result list, and it is removed from the frequency map to ensure it is not processed again. After processing all characters in order, any remaining characters in the frequency map, those not present in order, are appended to the result list. These characters are added in the order they appear in the frequency map, preserving their original relative order from S. Finally, the result list is joined into a single string, which is returned as the output. This approach ensures the desired sorting while maintaining efficiency. The algorithm is efficient, with a time complexity of O(n) plus m, where n is the length of S and m is the length of order. This is because we iterate through S once to build the frequency map, and we iterate through order and the remaining characters in the frequency map once more to construct the result. The space complexity is O(n), as the frequency map stores at most n entries for the characters in S. Here, we begin by defining a method called custom sort string, which takes two strings as input, order and S. The goal is to sort the characters in S based on the ordering specified in order. First, we create a frequency map to store the count of each character in S. This is done using a hash map, where the key is the character, and the value is its frequency. We populate this map by iterating through the characters of S and updating the counts accordingly. Next, we use a string builder to construct the result string. For each character in order, we check if it exists in our frequency map. If it does, we append it to the result string the number of times it appears in S, based on its frequency. Once processed, we remove the character from the map to avoid duplication. This ensures that the characters in S are added to the result string in the correct order as specified by order. After processing the characters in order, we handle any remaining characters in S that were not part of order. These are still stored in the frequency map. For each entry in the map, we retrieve the character and its count, then append the character to the result string as many times as its frequency indicates. This ensures that all characters from S are included in the final result. Finally, we return the constructed string by converting the string builder to a string. This approach ensures that the characters are sorted as specified by order, while preserving the remaining characters in their original frequency. To solve the problem, we start by building a frequency map of the string S. Here, the input string S is ABCD. As we iterate through each character, we count its occurrences and update the frequency map. For example, when we encounter A, it's added to the map with a count of 1. Then B is added with a count of 1, followed by C and D, each also with a count of 1. By the end of this step, our frequency map is A1, B1, C1, D1. Next, we construct the result string by following the custom order provided in order, which here is CBA. For each character in order, we check if it exists in the frequency map. If it does, we append it to the result as many times as its frequency and then remove it from the map. For C, we append it once, so the result becomes C, and C is removed from the map. Similarly, we append B and A, updating the result to C, B, A, and leaving only D1 in the frequency map. After processing all characters in order, we handle the remaining characters in the frequency map that were not part of the order. Here, the only remaining character is D, so we append it to the result, updating it to C, B, A, D. Finally, we join all the characters in the result list to form the output string. The final result is CBAD. This demonstrates how we use the custom order to prioritize certain characters while preserving the original frequency of all characters in S. Now, let's explore another example where there are extra characters in S that are not in order. For this case, the inputs are order equals XYZ and S equals ZYXXZZY. The first step is to create a frequency map for S. As we iterate through the string, we count the occurrences of each character. For Z, which appears 3 times, Y, which appears twice, and X, which also appears twice, the frequency map becomes Z3, Y2, X2. With the frequency map built, we now construct the result string based on the order in XYZ. Starting with X, we append it twice since its frequency is 2, updating the result to XX. Next, for Y, we append it twice as well, making the result XXYY. Finally, for Z, which has a frequency of 3, we append it 3 times. The result now becomes XXYYZZZ, and the frequency map is empty. Since there are no remaining characters outside of the custom order, we proceed to join these parts together. The final string is XXYYZZZ. This example demonstrates how all characters in S that are part of order are incorporated in the correct sequence, while characters not in order do not require additional handling here since the frequency map is already empty. In the last example, we handle a scenario where order does not include all characters present in S. Here, order is F and S is KVETBA. First, we build the frequency map for S. Each character in S appears exactly once, so the map is G1, F1, E1, D1, C1, B1, 1. Following the custom order AFK, we start constructing the result string. For E, we append it once, giving E, and remove it from the frequency map. For F, we append it once as well, updating the result to E, F. Then, for G, we append it once, making the result E, F, G. At this point, the frequency map still contains characters D, C, B, A, which are not part of order. These remaining characters are appended in their original order from S, resulting in E, F, G, D, C, B, A. After joining, the final string is F. This example highlights how we handle characters outside of the custom order by maintaining their relative order from the input string. To analyze the time complexity of this solution, let's break it down into stages. First, we process the input string S to create a frequency map. Here, we iterate through each character in S, performing a dictionary lookup and update for each one. Since dictionary operations like get and set are average O(1), the total time for this step is O(n), where n is the length of S. Next, we build the result string for the characters that appear in the order string. This involves looping through each character in order up to m iterations, and for each character, we check its existence in the frequency map in O(1). If it exists, we append it to the result list frequency char times, which takes O frequent char for the appends. Finally, the character is removed from the map, also in O(1). These operations are tightly bound to the frequency of characters in S, so the total time for this step will depend on both n and m. Now, since the total frequency of characters in S is bounded by O(n), the appending operation in step 2 collectively takes O(n). Adding the O(m) for the loop over order, the total time for this step is O(n plus m). Moving to step 3, we handle the remaining characters in the frequency map, those not present in order. Here, we iterate over the map, appending each character frequency char times to the result list. Since the total frequencies still sum to O(n), this step takes O(n). Finally, in step 4, we join the result list into a single string using .join. This operation is proportional to the total length of the strings in the list, which is the length of S, so it's O(n). Summing up all contributions, the overall time complexity is O(n plus O(n plus m plus O(n plus O(n), which simplifies to O(n plus m). Now let's look at the space complexity, starting with the frequency map. This map stores the unique characters from S along with their counts. In the worst case, all characters in S are distinct, so the space required is proportional to the number of unique characters, denoted as U. Since U is always less than or equal to n, the space for the frequency map is O(n). Next, we consider the result list, which stores the rearranged string. Its total length is equal to n, so it also requires O(n) space. Beyond that, we use a few additional variables like frequency and result, but these are constant in size and don't scale with the input. Therefore, the additional space is O(1). Combining these, the overall space complexity is O(n plus O(n), which simplifies to O(n). Bringing it all together, the overall space complexity of the solution is O(n), which accounts for both the frequency map and the result list. To compare, a naive approach might involve repeatedly searching for each character in order within S and appending matches to the result. Searching through S takes O(n) for each character in order, and with m characters, the total time complexity of this naive approach would be O(m*n). In contrast, the provided solution avoids redundant searches by using a frequency map, which reduces the complexity to O(n plus m). This optimization ensures that the solution is much more efficient, especially for larger inputs. Finally, let's analyze the best, average, and worst-case scenarios. In the best case, all characters in S are found in order. Here, the frequency map and the result list are processed in O(n plus m). In the worst case, none of the characters in S are found in order. Even in this case, the frequency map is processed in O(n), and all remaining characters are appended in the final step, making the total complexity still O(n plus m). The average case, which is a mix of these scenarios, also works out to O(n plus m, due to the linear contributions of each step. Mathematically, each operation dictionary lookups, updates, appends, and joining is bounded by O(1), or proportional to the input size. Summing these contributions gives a tight upper bound of O(n plus m), which is the final time complexity of this solution. When solving this problem, there are some common mistakes you might encounter. First, it's important to account for characters in the string S that do not appear in order. If you assume that every character in S will be in order, you risk missing characters in your output. Always ensure that all characters in S are handled, even if they are absent in order. Another common issue is using nested loops to perform the sorting. For instance, if you repeatedly scan S for each character in order, you'll end up with a time complexity of O(n*m), which is inefficient for larger inputs. Instead, aim for more optimized approaches. Lastly, trying to modify the input string S directly while iterating can be problematic. Since strings are immutable in many languages like Python and Java, this will result in either errors or unexpected behavior. To avoid this, work with a new string or a dedicated result structure. Now, there are additional mistakes to watch out for. One is failing to consider edge cases, such as when order or S is empty, or when all characters in S are identical. Overlooking these scenarios can lead to runtime errors or incorrect results, so always test with both minimal and maximal inputs. Another potential pitfall is misunderstanding the problem statement. Some might interpret order as requiring a strict sequence rather than a prioritization. However, the actual goal is to sort S so that characters appear in the order defined by order, not necessarily to rearrange them into an exact sequence. Understanding this distinction is crucial to implementing the correct solution. To perform well in interviews with this problem, there are several key insights to keep in mind. First, leverage data structures like hash maps or dictionaries. These can be used to count the occurrences of characters in S and then sort them efficiently based on order. For example, you can store frequency counts in a hash map and then iterate through order to construct the result. Additionally, prioritize time complexity. Your goal should be to achieve O, n plus m, where n is the length of S and m is the length of order. Avoid solutions that rely on nested loops or redundant operations. It's also important to clarify edge cases during an interview. For instance, if order is empty, should the output simply return S as is? Finally, recognize the conceptual goal of the problem. It evaluates your ability to combine sorting logic with custom prioritization, which is a common theme in string manipulation tasks. This problem is closely related to several others that you might encounter on platforms like LeetCode. For instance, LeetCode 451, Sort Characters by Frequency, shares the idea of sorting based on frequency or custom prioritization. Another example is LeetCode 49, Group Anagrams, which also relies on hashing and frequency counting to group or sort strings. LeetCode 937, Reorder Data in Log Files, involves custom sorting based on specific rules, making it another relevant comparison. And of course, revisiting LeetCode 791 itself can help refine your understanding and approach to the problem, as it ties directly to the concept of custom sorting. There are also alternative approaches to solving this problem, each with its own trade-offs. The brute force approach involves iterating through order and collecting all occurrences of each character in S. While this method is straightforward to implement, it's inefficient, with a time complexity of O, n*m. A more efficient approach uses a hash map to count frequencies of characters in S, followed by constructing the result based on order. This achieves O, n plus m, time complexity but requires additional space for the hash map. Another option is to use a custom comparator for sorting, where characters are sorted based on their indices in order. This method is elegant and concise but has a slower time complexity of O, n log n, compared to the hash map approach. Each method has its merits, and the best choice depends on the constraints and requirements of the problem. Thank you for joining us today. To summarize, we discussed the custom sort string problem, its brute force approach, and complexity analysis. We also highlighted key takeaways, including the use of hash maps for efficient sorting and when to apply this strategy. Make sure to like, subscribe, and share for more problem-solving sessions. See you next time, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!